Today we start one important topics related to non-linear space, especially Banach space. But we are discuss now LP space, obviously measure space. So we talk about this topic, measure space LPE. We know about convergence in measure. Today we start about LPE. LPE, we know about that set of all equivalence classes of set of p integrable functions. Okay, we discuss this one. Okay, this one be a Banach space. We discuss today this one be a Banach space. We know about that. Which space is called Banach? We know about that. Those norm space which are complete. This space is called Banach space. Okay, that means those space which are complete. Complete means those place which those norm space. Okay, norm space we write it in short. Norm space complete implies Banach space. Okay, and how again we also discussed in previous class also any absolutely convergent series, any absolutely convergent series, okay, is convergent. That means always not convergent, but if convergent, then obviously we talk about that this space be complete. Okay, this space, this norm space be complete. Okay, so we use this in here and we prove LP be a Banach space. So we start from early part. We also discuss this corollaries or theorems in previous class also. This one, this definitions, norm space, we know about norm space and obviously complete norm space, this means Banach space. And obviously we talk about absolutely convergent series and which series is convergent. We also talk it in previous class, and obviously we see about that in norm space, if absolutely convergent series implies convergent, then this one, that means this space be complete. Okay, so we also discuss now we discuss LPE be a Banach space. We start from proof, we write it in a manner. Okay, we erase that portion and going to prove of that. So we write here proof. We know that a norm space Y is complete. We know that a norm space Y is complete if and only if every absolutely convergent series, every absolutely convergent series in Y be convergent in Y, This one obviously one important theorem we also discussed in previous class also. Okay, we use this theorem here to prove LPE be a Banach space. That means Y be a complete space. Okay, we start about from here. Let summation Fn, okay, n equal to 1 to plus infinity be a series of elements, of LPE, okay, of LPE such that n equal to 1 to infinity norm of Fnp equal to m less than plus infinity. Okay, so we just let this one. Okay, then what that means we also discuss here. We discuss that define Sn equal to what? Sn equal to f1 f2 plus dot fn. nth partial sum. Okay, and we write here g of, okay, g of n equal to mod of fn, mod of f2, dot 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 mod of fn. Okay, that means some modulus of fn. Okay, partial sum of modulus of fn is represent gn, and partial sum of fn obviously represent nth partial sum, represent sn. Okay, then what we show that we write it here, we erase that portion and going to further discussion of that. Okay, we have to show that we have to show that Sn is convergent in LCE. We write here, we write norm of CNP equal to what? Norm of mod of f1 mod of f2 dot 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 mod of fn norm p equal less than equal to what? Less than equal to norm f1 p, norm f2 p, norm fn p. Okay, this less than equal to what? This less than equal to m for all n belongs to natural number. And we marked it what? We marked it here integration e norm of g and p d mu equal to integration of e here mod of gn whole to the power p d mu less than equal to m to the power p for all n belongs to natural number. Okay, we marked it 1. I understand. I think not a problem at all. Okay, g to gn to the power n, then this one is less than equal to m to the power p. Okay, okay, now we also write here, sorry, here not mod norm of gn. Okay, we write it this one. Okay, understand? Is gn to the power p or mod gn to the power p, then this one is right. Okay, I understand. Here we write, that means gn to the power p equal to norm of g to the power p, not a problem at all. Then we're going to here discussion that, note that, okay, note that here gn plus 1 equal to mod of f1 dot 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 mod of fn plus mod of fn plus 1. Okay, then this one equal to what? This one equal to gn plus mod of fn plus 1. Okay, for all n belongs to natural number. Understand? Then what happened? Then we erase our portion and going to further discussion of that. So why we write it here, Sn convergent in LP, we have to show that. Then we discuss this one, GP, this one, this one, GP is bounded Gn to the power p whole to this one less than equal to m to the power p. Okay, and obviously we discuss it. Okay, we discuss it. That means Gn here represents some monotonically increasing sequence of non-negative extended real valued measurable function on E. Okay, we write it now. We erase that portion and going to further discussion of that. So we write it now. Hence Gn be a monotonically increasing sequence of non-negative extended real valued measurable function okay, on E. Then what happened? Then Gn converges to a non-negative extended real value. Then Gn converges to a non-negative extended real valued measurable functions G on E. Okay, hence what happened? Hence by Leibniz monotone convergence theorem. Leibniz monotone convergence theorem we also discussed in previous class. Okay, Leibniz monotone convergence theorem, what we write? We write that limit n tending to infinity integration of E Gn whole to the power p d mu equal to integration E here limit n tending to infinity Gn to the power p d mu. Okay, this equal to what? This equal to integration E g to the power p d mu less than equal to what? Less than equal to m to the power p. We write it in 1, so we write here from 1. Okay, so this one we marked as 2. Okay, hence what we write here? We write this one G belongs to this, implies that G belongs to LPE. Okay, also obtain this one, G belongs to LPE. Okay, I think not a problem at all. Then we erase that portion and going to further discussion of that. Okay. Now we define some a equal to what? A equal to x belongs to E such that gx belongs to closed 0 plus infinity. Okay. And b equal to what? B equal to x belongs to E. Okay. Gx equal to infinity. Then what happened? Then for x belongs to A, okay, n equal to 1 to infinity mod of fn x equal to what? Equal to gx belongs to what? Belongs to 0 plus infinity. Okay. Then this implies what? This implies summation n equal to 1 to infinity mod of fn x be convergent. This implies what? This implies n equal to 1 to infinity fn x be absolutely convergent. Be absolutely convergent. Okay. Then just for x belongs to A we discuss now. Okay. Then we talk about that. We know that every absolutely convergent series series of real numbers is convergent. Series of real numbers be convergent. Okay. We also discussed in earlier. That means this one some BSc level problem. Okay. BSc mathematics level problem. Every absolutely convergent series of real numbers be convergent. But in norm space this one not happen. We also discuss then in previous class also. So we talk about that. Then here convergent. So now we erase and going to this right here. Proceed further. What? Then there exists a function. If e2 minus infinity plus infinity such that fx equal to limit n tending to infinity Sn x if x belongs to A and plus infinity if x belongs to B. Now we have to show that A belongs to LPE. Okay, and norm of Sn difference fp tends to 0. Okay, so what we write here? We write this one Sn difference fp converges to 0. Okay, now we're going to do that. Note that norm of Sn x equal to mod of f1x f2x dot fn x. Okay, less than equal to norm of f1x mod of f2x dot mod of fn x equal to gnx for all x belongs to A, taking limit as n tending to infinity taking limit as n tending to plus infinity, we get what? Mod of fx less than equal to mod of gx. Sorry, gx. Okay, for all x belongs to a. Okay. Then what happened? We erase our portion and going to further discussion of that. Then what happened? Then we write it here, integration of e mod of fx whole to the power p d mu less than equal to integration of e g to the power p d mu less than equal to m to the power p for all x belongs to a. Okay, from 1. This implies that a belongs to LPE. Now what? Now Sn difference f whole to the power p x equal to, here we write Sn x difference fx. Okay, whole to the power p. This less than equal to mod of Sn x plus mod of fx whole to the power p. Okay, this less than equal to gx plus gx whole to the power p. This equal to 2 to the power p gx whole to the power p. Okay, for all x belongs to a. Done, I think. Then what happened? Then we write this one here, integration of e mod of Sn difference a whole to the power p d mu. Okay, less than 2 to the power p integration of e here g to the power p d mu. Okay, less than equal to 2 to the power p m to the power p. Okay, for all x belongs to a. Then what happened? Then we write here Sn, this implies Sn difference f belongs to LPE. Okay, now we erase that portion and going to further discussion of that. Here Sn a difference f, okay, is a sequence of measurable functions, is a sequence of measurable functions, okay, such that Sn difference f converges to 0 and obviously mu almost everywhere on e. Okay, then what happened? Then by Lebesgue convergence theorem, what happened? Integration of Sn difference a whole to the power p d mu, okay, converges to 0 with respect to e. Then this implies that Sn difference a whole norm p, okay, converges to 0. Thus what happened? Thus the absolutely convergent series Fn converges to f. Thus the absolutely convergent series. Absolutely convergent series summation n equal to 1 to infinity fn converges to an element A belongs to LPE. Okay, therefore LPE be complete. I think that means we discuss this one. Okay, so what we do, we have to prove that LPE norm P be Banach space. Okay, so we also discuss that means Fn some series of elements of LPE, that means the summation norm Fn, that means equal to m less than plus infinity. Obviously we discuss about that Sn and Gn be the nth partial sum of Fn and mod Fn. Then we have to show that Sn converges in LPE. So we first show that GNP less than equal to m, and next show that Gn whole to the power p d mu